Hello everybody, good morning. Myself Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of the sixth module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall begin with the concept of linear equation solvers. We shall classify the linear equation solvers in the direct and iterative methods, and then we shall elaborate upon the Gauss elimination method. So first, we classify the linear equation solvers, and before that, we define what are the linear equations. So, the linear PDEs lead to a linear or a system of linear algebraic equations. If Ax equals to B is a system of matrix equations, then A not equals to function of x or the function of degree of freedom signifies a system of linear algebraic equations. If A is a function of x, then Ax equals to B. This leads to Axx equals to B is a system of nonlinear algebraic equations. The nonlinear PDEs or ODEs lead to nonlinear matrix equation systems that are first linearized and then only linear equation solvers can be used. The Laplace and Poisson equations are examples of linear PDEs and lead to linear algebraic equation system AT equals to B, where A is not a function of the degree of freedom or the entries of matrix A are constants. The Navier-Stokes equations are nonlinear and hence the matrix equation systems generated from these equations are also nonlinear. Linearization is performed for application of the linear equation solvers for such cases. So, in case of the Navier-Stokes equations of motion, our coefficient matrix, it is a function of q, v and p, and the degree of freedom, if I say that is x, this x is also a function of q, v and p equals to b. So this is the appearance of a system of nonlinear matrix equation system. This is the DOF vector. This is the coef matrix. It means that for nonlinear systems, the entries of the coefficient matrix depend on the degrees of freedom. So the linear equation solves the Ax equals to b system only when A is not a function of x, or when the matrix equation system is linear. Now we classify the linear equation solvers. Linear equation solvers, they are classified as direct methods, so from linear equation solvers we find x from the system Ax equals to b. Ax equals to b, its appearance is Ax equals to b, where A is n by n square matrix, x is n by 1 degree of freedom vector, and b is n by 1 load vector. So our purpose is to find x, n by 1. So the linear equation solvers, they are classified in two fundamental types: direct methods, iterative methods, and we have a combination of direct and iterative methods that has limited use, that is known as the combined methods. We say that combination of direct and iterative methods. So a method known as the line by line method is a prominent example of this hybrid method. So line by line method, widely used in the finite difference and finite volume methods. This is an example of this hybrid method. As the name indicates, the line by line method requires a structured mesh. We need the grid lines in the mesh, and because of that, for unstructured mesh applications, this line by line method, it cannot be used. Now these direct methods, we can classify them in two approaches: one for solving symmetric matrices, And this other one, the main branch, is solving symmetric as well as asymmetric matrices. These iterative methods, they are classified into three types. The first type is known as stationary iterative methods. Stationary iterative methods. The second one is known as non-stationary iterative methods. And the third one is known as the multi-grid method. So we provide further details here. So linear equation solvers. So purpose is find x from ax equals to b. So we have already classified them. This is for direct, this is for iterative, and this is for combination of direct and iterative. For the direct methods, we have for symmetric matrices, then we have other class for symmetric and asymmetric matrices. For the symmetric methods, we have the Cholesky decomposition. Cholesky decomposition. In the common methods, the most prominent method is the Gauss elimination. So we have Gauss elimination, then a special class of Gauss elimination that is known as Thomas algorithm. Thomas algorithm, Crowd's method, LU decomposition, L for lower triangular matrix, U for upper triangular matrix. Then we have Gauss-Jordan method, and so on. For the iterative methods, we classify them as stationary iterative methods. Under stationary iterative methods, we have two prominent methods. One is known as the Gauss-Seidel iterative method. The second one is known as the Jacobi iterative method. And the third one, briefly it is written as SOR. We say this is successive over relaxation. So SOR, the full form is successive over relaxation. In the iterative method, the second portion is non-stationary or Krylov space methods. Under this group, we classify these methods as for symmetric matrices, and the other one for asymmetric matrices. For symmetric matrices, the prominent example is the conjugate gradient method. Under asymmetric methods, we have biconjugate gradient method. Briefly, we write it as BICG. Then we have biconjugate gradient stabilized. So we say it as BICG stab. And we have GMRES. In the iterative method, we can include the multigrid method. And for the combined direct and iterative methods, already we have mentioned that the line-by-line method is a common example of this hybrid method, which is an application of point Gauss-Seidel method as well as the direct method, such as Thomas algorithm. So here, BICG, it stands for biconjugate gradient. BICG stab, it stands for biconjugate gradient stabilized. And GMRES, it stands for generalized minimal residual method. This method was developed by Saad and Sulj in 1986 for asymmetric matrices. Now BICG stab and GMRES, both of them operate for the asymmetric matrices, but BICG stab, its convergence is non-monotonic in nature, whereas for GMRES, the error decays in a monotonic fashion. So here we distinguish between the direct and iterative methods. So comparison of direct and iterative methods. Direct method, iterative method. These direct methods, these are single step methods. In iterative methods, we repeat our calculations. Multi-step methods, where similar calculations are repeated. The direct method is not suitable for large size matrices, not suitable for matrices of large size. Iterative methods, they can handle both small and large matrix equation system, suitable for small as well as large sized matrix equation systems. In direct method, no initial guess is required. In iterative method, initial guess is compulsory. In direct method, there is no concept of convergence. These solutions converge by default if the calculations are correct. In iterative methods, convergence is the crucial step that governs acceptance of the solutions. In direct methods, the memory requirement for the computer is very high. In iterative methods, the computer memory requirement is smaller as compared to direct methods. In direct methods, parallelization is difficult. Parallelization is difficult for the computer program. In iterative method, parallelization is easy. In direct methods, we have to store the zeros present in the coefficient matrix. Zeros in the coefficient matrix are stored. In iterative method, zeros in the coefficient matrix are not stored. Coefficient matrix are not stored. Now, when we talk about the solvers in a CFD sense or FEM sense, we talk about the discretization technique. So, given PDE or ODE, it gives us AX equals to B. This process is known as discretization. This discretization process is known as the solver. So, this is solver. Maybe FEM, FVM or FDM. When we talk about linear equation solvers, then the role of linear equation solver is only there when we have the matrix equation system available. So linear equation solver is not the flow solver or the heat transfer solver. This is a big difference we have to remember, that linear equation solvers, it is only for finding the degrees of freedom from the matrix equation system. Now apply linear equation solvers, find X. Now we illustrate the development of the Gauss elimination algorithm. Gauss elimination is the primary direct method. Gauss elimination is the primary direct method of solving AX equals to B, where A is non-singular. Gauss elimination is applicable for both symmetric and asymmetric square matrix equation systems. Let us consider that matrix A is diagonally dominant and it contains no zero along its diagonal. The operation count of Gauss elimination is of the order of n cube by 3. the operation count that gives roughly the number of multiplication, division, addition, and subtraction during the calculations of Gauss elimination method is of the order of n cube by 3, where n is the order of the square matrix. The primary drawback of Gauss elimination method is that it suffers from round of error in case of large matrix systems. The major drawback of Gauss elimination is that it suffers from round of errors for large system of equations and results in poor solutions. So we shall consider the case of Gauss elimination without pivoting. It means that we consider that in all the rows, the diagonal term, it is dominant, and because of that, there is no swapping of rows required to make the matrix diagonally dominant. So let us develop the Gauss elimination algorithm with respect to a small matrix. Development of Gauss elimination without pivoting. Let us consider a small matrix equation system Ax equals to b of 2 by 2 size. The main steps of Gauss elimination are: the first step is forward reduction. This step reduces the given matrix to an upper triangular matrix. A form that is also known as the row reduced echelon form. The product of the diagonal terms in the row reduced echelon form provides the determinant value of the given matrix. In the second step, we perform back substitution. Back substitution to calculate the unknown quantities. So we consider a system of linear algebraic equations where the matrix size is of 2 by 2. So here we have Ax equals to B such that A equals to 2 by 2 matrix, B is X is 2 by 1 vector and B is also a 2 by 1 vector. So these equations we can write as A11x1 plus A12x2 equals to B1, A21x1 plus A22x2 equals to B2. So this is the original form. Desired form after forward reduction is A11x1 plus A12x2 equals to B1, A22-x2 equals to B2-. So this 2 by 2 matrix equation system has reduced to an upper triangular matrix in the left hand side after the row reduction or the forward reduction. Then certainly we can find out the term x2 by back substitution. So after the row reduction, the second equation, it has changed this coefficient for x1, it has been eliminated. So it indicates that in the Gauss elimination step, we keep the first equation as the reference equation and we do not change the first equation, and then we perform the row operations for the second, third and up to the nth equation. We get an n by 1 upper triangular matrix equation system where the last equation gives only single degree of freedom, and from there we can calculate xn, and this xn, it gives us xn minus 1, xn minus 2 and eventually x1. So we can represent this matrix equation system in the echelon form by eliminating the A21 term in the original system of the governing equations. These equations we identify as equation 1 and the other one we identify as equation 2. Here this is x2. Equation 2 is rewritten as original equation 2 into A11 minus equation 1 into A21. So this gives us the equation 2, it will become A11 A21 x1, A11 A21 x1 plus A11 A22 x2 equals to A11 B2. This is our new second equation, and our original first equation, this we multiply with A21, then we get A11 A21 x1 plus A12 A21 x2 equals to A21 B1. Now this subtraction, it eliminates the first term and we are left with A11 A22 minus A12 A21 into x2 equals to A11 B2 minus A21 B1. Now our desired form was A22 x2 equals to B2 It means that this portion, this represents A22 and this portion, it represents B2 Now A22 equals to A22 plus correction term, and similarly b2 dash equals to b2 plus correction term. To get the relationship between a22 dash and a22, we divide both sides of this equation by a11. Divide both sides by a11 to get a22 minus a12 a21 by a11 into x2 equals to b2 minus a21 b1 divided by a11. So we got our a22 dash and b2 dash. So a22 dash equals to a22 plus correction. Here we get the correction term as minus a12 a21 by a11, and similarly we get the correction term for the b2. Now this a22 dash and a22, this relationship, this provides us with a generic relationship. So here we can develop a generic relationship for the transformed value of any term by expanding this relationship. So for a 2 by 2 matrix, upper triangulation requires one step. So in one step of calculation, a 2 by 2 matrix, it reduces to the upper triangular form. Therefore, for an n by n matrix, upper triangulation will be achieved in n minus 1 steps. So this n minus 1 step, we define a new parameter denoted by k. So the number of steps be denoted by k. Therefore, k equals to n minus 1 or n equals to k plus 1. Now, in a matrix capital A equals to Aij, I is the index for row and j is the index for column. Now, a22 dash equals to a22 minus a21 into a12 by a11. Now we take I equals to 2 and j equals to 2. This gives us aij equals to aij minus ai. We keep the space for index 1 as blank for the time being, and then we go for a. Again we keep the index for 1 as blank, and then we have 2 for j, and then we keep the denominator as a. Now the first portion a dash ij, in this case I and j act as free indices. So in the right hand side, the first term, here also I and j are free indices. Therefore, in this last portion, I and j are free indices and hence must not be repeated. It means that we have to use a different index for 1. Now, the only index left in our calculation, that is the number of steps, and that is small k. So here, the number of steps will come here, and 1 is present here 4 times. So k will be appearing 4 times, and k will act as a dummy index since it is repeated and it is not having extra time presence. Because of that, here we write it as k, k, k and k. So finally, the generic term after row reduction becomes Aij equals to Aij minus Aik into Akj divided by Akk. Here k is varying from the 1 to n minus 1 steps we calculate for reduction of nth order matrix. So k is varying from 1 to n. When we go for the index 1, we look into the 2 by 2 matrix. So here this is 2 by 2 matrix A11, A12, A21, A22. This reduces to A11, A12, 0, A dash 22. It means that for k equals to 1, the terms that we deal, that is greater than k. So it means that in that case, I equals to 2 and j equals to 2. So it means that I is k plus 1, and here since our order is 2, so it is remaining as k plus 1, and j is also 2 for the k a dash 22 term, and because of that the index I and j both are varying from k plus 1 up to the last row, and for j it is varying from k plus 1 up to the last column. So with this indices, our row reduction formula can be converted in a pseudocode. So pseudocode for row reduction becomes do k equals to 1 to n minus 1, do I equals to k plus 1 to n, do j equals to k plus 1 to n, aij equals to aij minus aik into akj by akk. So end do and do. So in the row reduction step, we see that there is a division by akk, which is a diagonal term, and division by the 0 is not permitted, and because of that no 0 should be present in the diagonal term. Here certainly the range is 1 to n minus 1 for k. For the back substitution, let us consider the augmented matrix of size n by n, A11, A12 up to A1n, A21, A22 up to A2n, AN1, AN2 up to ANN. Here the degree of freedom is x1, x2 up to xn, and the right hand side load vector is b1, b2 up to bn. Now this load vector we can consider as part of the last column of this A matrix. So we can rearrange the matrix A may be augmented as A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. Then we can insert the column vector for the right hand side as B1, B2 up to Bn. So for this column, this matrix is now of having one extra column. So this is having the order of n into n plus 1. So these last terms or the column vector in the last, we can represent it as in terms of A. So we can write them as A1 n plus 1, A2 n plus 1, An n plus 1. So this is the augmented matrix. So the augmented matrix may be rearranged as A11, A12, A1n, A1 n plus 1, A21, A22, A2n, A2n plus 1, AN1, AN2, ANN, AN n plus 1. So this becomes a rectangular matrix with n rows and n plus 1 columns, n into n plus 1, and our degrees of freedom, they were x1, x2 up to xn. With this, the forward reduction pseudocode will have the range of j from 1 to n plus 1 instead of 1 to n. So we have do k equals to 1 to n minus 1, do I equals to 1 to n, these are rows, these are number of steps, do j equals to 1 to n plus 1, these are columns. So our aij equals to aij minus aik akj by akk, aik akj by akk, and do and do and do. So for the augmented matrix, we have rewritten the pseudocode for the forward reduction. Here for I, the range is k plus 1, and similarly for j also, the range is k plus 1. For back substitution, the augmented matrix looks like, in the first row we have A11, A12, A13, A1n, A1 n plus 1. This is for the augmented portion, A n plus 1. Now for the last row we have A n n, this is A dash, and here in the right side it has A dash n n plus 1. So this is the diagonal term. All the sub-diagonal terms, they are 0. Then in the Second equation from the back side, we have a dash n minus 1 n minus 1. Here we have a dash n minus 1 n. Here we have a dash n minus 1 n plus 1. In the third equation from bottom, we have a dash n minus 2 n minus 2, a dash n minus 2 n minus 1, a dash n minus 2 n, a dash n minus 2 n plus 1. We complete the matrix here. So this is n row, n plus 1 column. Then our degrees of freedom are x1, x2, x n minus 2, x n minus 1, then xn. Now, if we look into the last equation, then we have from the last equation a dash nn into xn equals to a dash n n plus 1. This gives us xn equals to a dash n n plus 1 divided by a dash nn. Now, to show the complete process, we consider the third equation from the back side. The third equation from the lower end or the n minus 2th equation gives a dash n minus 2 n minus 2 x n minus 2 plus a dash n minus 2 n minus 1 x n minus 1 plus a dash n minus 2 n xn equals to a dash n minus 2 n plus 1. Now, to make the expression simple, we shall consider n minus 2 as I. So make it n minus 2 equals to I, or n equals to I plus 2. In this expression, when we come to the third equation from the bottom, we already calculated xn and xn minus 1. These known terms, they will be shifted to the right hand side. So xn already known and xn minus 1 already known when we are going to calculate xn minus 2. So this is the direction of calculation, direction of finding xn values. So here a dash n minus 2 is I, xi equals to a dash n minus 2 is I. So n is I plus 2. So n plus 1 is I plus 3. So a dash I plus 3 minus the two summations, two terms will be added up. This is a dash I. So n minus 1 is I plus 1. N minus 1 equals to I plus 1. So a dash I n minus 1 is I plus 1 x I plus 1 minus a dash n minus 2 is I. So n is I plus 2 x n is I plus 2. So this gives us a dash I plus 3 minus summation a dash ik xk, where k equals to I plus 1 to I plus 2. Now I plus 2 is n and I plus 1 is n minus 1. So here we have a dash I xi equals to a dash I plus 3, this is n plus 1. So a dash I n plus 1 minus summation of k equals to I plus 1 to n. I plus 2 is n a dash ik xk or xi equals to 1 by aii into a dash I n plus 1 minus summation over k equals to I plus 1 to n a dash ik xk, where I is varying from n minus 1 to 1, where I equals to n minus 1 to 1 in steps of minus 1. The back substitution process can be summarized as the back substitution can be coded as xn equals to a dash n plus 1 divided by a dash nn, do I equals to n minus 1 to 1 in steps of minus 1, xi equals to 1 by aii into a dash I n plus 1, a dash I n plus 1 minus summation over a dash ik xk k equals to I plus 1 to n and do. We conclude today's class here. We have classified various types of linear matrix equation solvers. We have compared the direct and iterative methods. Finally, we have provided the pseudocode for Gauss elimination method without pivoting. For today's class, I recommend the texts by Professor Tanhill et al., Professor Patankar, and Professor J.D. Anderson. Thank you very much for attending this class.